In this video, we'll be discussing the last of the topics from Chapter 5 that you all are responsible for, and that would be chemical means of microbial control. Starting out here, we just want to take a look at some of the chemicals that are used to destroy these microbes. They're kind of grouped based upon their effectiveness. So we've talked about different types of instrumentation, critical versus semi-critical, things like that. And now we're going to try and relate some of these different chemical used for control to the instruments that they can be used to attain control over. So first we have sterilants. Remember, sterilization involves the removal of all vegetative microbes along with viruses and endospores. And the sterilants are usually used to control heat-sensitive critical instruments. So if you cannot autoclave a particular item, then you could use a sterilant to try to achieve microbial control. High-level disinfectants destroy viruses as well as vegetative cells, as it says here in the slide. Remember, disinfectants don't necessarily have to kill all vegetative organisms and endospores. They won't, as it says here, reliably kill those endospores. So semi-critical instruments, things that typically come in contact with mucous membranes, that's what you would see these high-level disinfectants utilized to achieve control over. Intermediate level disinfectants, you can see up here, destroy vegetative bacteria, mycobacteria, fungi, and most viruses. So by contrast, we could say they would not be able to destroy endospores or all viruses, and those would be used to disinfect non-critical instruments, things that would come into contact with unbroken skin and so forth on. Low-level disinfectants destroy a good amount of microbes as well, fungi, vegetative bacteria, but it would not include mycobacteria or enveloped viruses. As it says there, they do not kill endospores, and you would typically see these used in household settings to disinfect things like furniture, floors, and walls. When we consider the effectiveness of these germicidal agents, they're regulated by potentially two different government agencies: the Food and Drug Administration, or the FDA, along with the Environmental Protection Agency, or EPA. You definitely, as it says here, should follow instructions regarding things like dilution of these various germicidal chemicals, as well as the temperature and duration needed for effectiveness. All of these things can influence the overall control that's achieved if it's too dilute or too concentrated, if the temperature utilized may not be correct, and if the duration of time is not used, or rather applied adequately as well. You should definitely try and clean objects. If you're going to use a germicidal agent on them, you want to try and make sure they're free of any dirt, debris, or oil before placing that germicidal agent on them. When it comes to selecting the appropriate germicidal chemical, several different factors have to be considered. We like to consider toxicity. Many of the chemicals can possibly be toxic to the human body as well as the microbes that you're trying to achieve control over. So you have to kind of weigh the risk of use versus the benefit of that. Is it more beneficial to not use it versus using it, depending upon the potential harm or side effects or harm that it may cause? We have to consider the activity and the presence of organic material being any material that contains carbon. Obviously, human beings being organic life forms, we don't want to interrupt those organic molecules that make up and comprise our cells. So we have to absolutely consider that as well. Compatibility with material being treated. As you can see here, liquids, for instance, could not be used on electrical equipment. Could you use heat in order to sterilize or disinfect some type of heat-sensitive material like a plastic? No, you wouldn't want to do that. So you have to definitely consider the compatibility. Residues that might be left behind, are they toxic or corrosive? If it's some type of medical device, we don't want it to necessarily be corroded due to our disinfecting or control of microbial treatment. Cost and availability, these are very relevant as far as industrial concepts are concerned. If you look at industry, obviously things are about keeping costs low so that you can pass that on to the consumer. So if a process is more costly or more scarce or harder to get, then it might be detrimental in the case of some industrial standards. Storage and stability, if you look at it, a lot of these chemicals are stored long term, so we definitely want them to be able to hold up. And then we also consider the environmental risk. What are the risks to the environment of using that in some cases you may have to neutralize an agent before you're able to properly dispose of it, or even dispose of it in a special manner. So now we want to take a look at some of these classes of germicidal chemicals, and the first one up are the alcohols. The alcohols usually are not 100% alcohol, I'll say that. Usually they work better when they're mixed with a slight bit of water or their concentration is diluted. So anywhere from a 60 to 80% mixture with water of ethyl alcohol or isopropyl alcohol. This is most commonly the alcohols that you'll use for first aid intervention, and you find them in any drugstore or anything or places like that. As you can see here, it kills vegetative bacteria, but definitely not reliable when it comes to endospores and non-enveloped viruses. That's because if you look at it, the manner of action for many of these alcohols is that it damages mucous membranes. Biological membranes. So that phospholipid bilayer associated with many organisms is disrupted when introduced into an environment where alcohols are contained. You can see the alcohols also denature proteins, but ultimately it is definitely critical to keep in mind that the alcohols are more effective in the presence of water. So as it says up here, pure alcohol less effective. The reality is that, as you see here, the proteins are more soluble in water, so it's easier for the proteins to mix with the alcohol. And also, as the membranes are damaged, the water within the mixture would also lead to cytolysis. So both are beneficial from that aspect. You can see up here commonly used as an antiseptic and disinfectant. If you consider some of the advantages of it, it is non-toxic, it is inexpensive, and it doesn't leave any residues. It doesn't leave any residue because the mixture evaporates quickly. Alcohol typically has a very relatively low boiling point, so it doesn't stay in that liquid form once it contacts surfaces very long. It evaporates very quickly. The drawback to it, well, if we consider compatibility, it can damage rubber, some plastics, and others. So you wouldn't want to use this long term on plastic type materials that had to be upheld. In a lot of cases, you may see a tincture. A tincture is an antimicrobial chemical dissolved in alcohol, and these are commonly used in most hospital settings. Aldehydes are up next. Aldehydes include things like glutaraldehyde, formaldehyde, and orthophthalamide, OPA. As you can see up here, the manner in which the aldehydes work would be to inactivate proteins and nucleic acids. This would slow down enzymatic reactions along with destroying genetic information in a number of different microbes. Typically what we see utilized is a 2% alkaline glutaraldehyde. That's usually used as a sterilant. Typically this requires the immersion of whatever items you're trying to sterilize for anywhere from 10 to 12 hours. So it does have a very long time for usage. Remember, from our earlier slide, I did mention that we definitely need to pay attention to the duration for which we'll use a particular item. It is toxic, so the items that are sterilized do require thorough rinsing after use. You can see the OPA is a little bit less toxic, but it does have a really adverse side effect. It turns skin gray, so most people don't like to use that. And formaldehyde is usually used as either a gas or what's called formalin. Formalin is used in many cases to preserve specimen. It can also be utilized from a medicinal standpoint in pathology for, once again, preserving the specimen. But the biggest drawback to using formaldehyde in any form is that it is a carcinogen. Biguanides, these chemicals, the most common of which is chlorhexidine, usually seen in a lot of over-the-counter products such as skin creams and mouthwashes. It's because it's a very effective antiseptic. It can come in contact with the skin and mucous membranes, and it does have a very low toxicity. It'll kill most vegetative bacteria, fungi, and also some enveloped viruses. Ethylene oxide. Ethylene oxide is a gaseous sterilant. We see this utilized in many cases for materials that are heat sensitive. So plastic items used medically that would have to be considered critical instruments. In a lot of cases, ethylene oxide gas would be utilized. Method of action for ethylene oxide gas is that it basically reacts with the proteins to destroy the microbes. Obviously, since it's a sterilant, it can also destroy endospores and viruses. Penetrates pretty well. Fabrics, equipment. You can see also implantable devices. So that would lead to its usage in a number of different arenas, such as electrical equipment, if it had to be, for instance, a pacemaker installed, or even artificial joints such as a hip. Used for a lot of different laboratory purposes as well. Many petri dishes, which are plastic, and also plastic pipettes, are sterilized using ethylene oxide gas. Limitations: it's flammable, so it is explosive when it's collected in large amounts. It's toxic, and it could be potentially carcinogenic. The halogens react with proteins and cellular components. The most common halogen, by the way, halogens are a group of chemicals on the periodic table. The most common halogen that's utilized is, well, chlorine. Chlorine bleach typically is going to be what we most commonly see, and it's usually recommended to use that in a dilution with water in order to cause it to be more effective. As we can see here, it is a disinfectant, so it would not be a sterilant. The drawback is that it can be irritating to skin and mucous membranes. Just think if you've ever cleaned your house and maybe you've gotten a whiff bleach, if you were cleaning it with bleach, that is, the irritation to your mucous membranes usually triggers a very violent coughing reflex. We do use chlorine extensively, typically also to disinfect water, especially municipal drinking water. So although it is very effective, you can see some oocysts, which are the dormant form of protozoans, and also the Giardia, Cryptosporidium and Giardia, both of these are protozoans. Some of those cysts do possibly survive and could cause diarrheal infections that way. Continuing with the halogens, iodine. Iodine is also used quite commonly. It's also used more commonly, I should say, in a tincture. Have you ever seen things like betadine? That's usually a tincture of iodine, and it's going to be more are rather easily applied in those scenarios. Iodophores are a little bit easier on the skin than the tinctures of iodine. It usually mixes iodine with some sort of organic carrier molecule, and that decreases the irritation. So as we moved away, we're using more of the iodophores at this point. Commonly, you'll see Pseudomonas be able to survive it. So although these iodophores are used commonly in hospital-based settings, they're not very effective combating Pseudomonas infections. Next up, metal compounds. A number of different ones. The most common one that we usually see would be silver. Silver is used in a number of different cases to try and achieve microbial control, especially with things like burns. And you can also see silver nitrate drops placed usually into the eyes of a newborn, especially if the mother is suspected to have some sort of gonorrheal infection. That silver nitrate is usually utilized to prevent that. At high concentrations, like most metals, this would be too toxic, so we usually use it in very low dosages, obviously. Next up would be ozone. Ozone, O3, it's the same type of ozone that you see in the atmosphere. It is a gaseous disinfectant, and most commonly, if you've ever been hiking or camping, there's not uncommon to see ozone tablets utilized to try to disinfect drinking water that's gathered from rivers or lakes or some other outdoor source like that. It works by oxidizing free radicals and ultimately killing microbes that way. Peroxygens, these are powerful oxidizers, also used as sterilants. The most commonly one seen would be hydrogen peroxide. Typically very effective against anaerobic organisms. The effectiveness with humans is a little bit debatable, because at the end of the day what happens is our human cells actually can process hydrogen peroxide, break it down into oxygen and water. So the effectiveness is a little bit decreased, because ultimately you would not have the hydrogen peroxide present for very long periods of time. As it says here, it is effective on inanimate objects because, well, obviously being inanimate, non-living, they would not be able to produce the catalase necessary in order to break down hydrogen peroxide, allowing it to stay present longer. Hot solutions are usually utilized to achieve sterilization of inanimate objects. There is also peracetic acid. It is, as it says here, more potent than hydrogen peroxide. It will sterilize in under an hour, and it is effective in the presence of organic compounds, such as human tissue. Phenolic compounds would be up next. these are highly irritable to the skin, so there is a significant drawback from that standpoint. They work by destroying cell membranes and denaturing proteins. Recently, some of these newer phenolic compounds, such as hexachlorophene and also triclosan, which have been used for years in many common over-the-counter products, have began to become more limited due to the fact of them potentially being irritants to the skin and some other mucous membranes. Quaternary ammonium compounds, or what are also known as quats, these cationic detergents are found in a number of different personal care products. Their benefits is that they have a very low toxicity, and they're really useful in disinfecting food preparation surfaces. Pseudomonas does resist those quats, the presence of them, and it can grow in those solutions of quats as well. The next few slides basically detail a summary, a couple of slides here, of the various chemical categories. As I told you before, definitely want to identify the various chemical categories along with the more common examples, and then I would also kind of jump over to the opposite side and see some of the situations in which they're used. So we talked about much of this already, so I won't reiterate this. This is just, so to speak, a quick summary of where you can see it. Lastly, here we have the preservation of perishable products. A number of different ways to try and preserve perishable products. We've even mentioned some already, such as the pasteurization, but that was more of a physical form, obviously. So when it comes to chemicals, you do have chemical preservatives. They usually obviously prevent or slow the growth of microbes and therefore extend the shelf life. Key thing though is that they have to be non-toxic and safe for ingestion, and that's dependent upon what authors you read, so somewhat debatable. There are weak organic acids, benzoic, sorbic, and also propionic acid. They do affect cell membrane function, and in many cases they're added to food products to help control molds and bacteria. Then nitrates and nitrites used in a lot of cases with processed meats. These have come under some focus recently because they have been proven to be somewhat carcinogenic due to being converted by intestinal bacteria. But they are effective at preservation. They do help stop the growth of Clostridium botulinum, and the higher concentration usually gives meat a very much more pinker color. There's another way to try and preserve foods. I didn't actually include it in here, but it would be chemical as well. For instance, like salting. Salting meats and things like that would also be a chemical form of preservation. So that kind of wraps up here the chemical means of control, and we'll conclude chapter 5 with this discussion.